Good. Okay, so welcome back, everyone. I hope you had a good first half of the week. So last time we were talking about we were basically reviewing classification, and we were looking at few pieces, few components that are kind of important pieces in a machine learning training, process. So basically, you need to know the data, you need to know the loss function, and sometimes it's also coupled with the model class that you're going to optimize, and then the fourth component being the optimization technique itself. And we had some, a good discussion on, hey, what's the dimensionality of, let's say, an observation, what's the dimensionality of your parameters, and so on. So we'll recap that, and then go on to what we left out in the first module, which is backpropagation. Uh, it's just basically chain rule in calculus for those of you know it, but we'll certainly start from scratch and revisit that. Okay. Um, so what I did, I just wanted to, before we get into the content, backpropagation and new things today, for this session, I wanted to just point out a couple of minor updates on the syllabus page. In particular schedule, what I've done is remove the dates. That's because basically, for example, some topics like backpropagation is actually being covered on the second day, right? There's a second week and so on. So we'll not try to rush through this material, because we always have, for example, we can drop some things at the end. But it's important that everybody is on a firm foundation with both Python and some of the more, I would say, basic models in deep learning. So we'll do our own pace, but the ones with the dates are basically the assignments and the project check-ins. Okay, so even if we, for example, miss, let's say, in CNNs, which we were hoping to touch today, even if we miss CNNs themselves or maybe parts of it, we're gonna continue with doing them in the subsequent weeks. Okay, so we'll roughly follow this order, but I've just basically removed the dates on the at least the lecture topics or the module topics. Okay, so um, and slides and all, everything else remains the same. Let me go to goals. So um, sorry, it's a different one. Okay. Um, yeah. So the goals for last time were to understand the key components of a classification task. So this is basically a recap of things that you might have seen in 572 or 575 or elsewhere. So from our perspective for this course, you just need to know that you just need to know those four components. There's a lot more that goes on when you talk about classification models. For example, in 572, you might have spent some time on model diagnostics, right? I mean, once you train a model on a specific data set, you would have spent some time on understanding how the model performs, what are its shortcomings and so on. But for last week's discussion, we were focused on the four key components, basically data models, optimization, and objective function. Okay. Um, we also discussed very briefly the motivation or the structure of the course, basically working with unstructured data being a key thing, as well as tying predictions to decision making. And within decision making, we're going to look at sequential decision making and so on. Okay, so that was some of the key ingredients of this whole course that we had a brush with. Today, we'll continue with this third goal, which is to understand how chain rule works. I think some of you already know this, but we'll recap this. We'll get into some detail with some small examples. And then we'll switch over to a little bit, get our hands dirty in terms of using Python. So I think last time I alluded to a good resource, which is Colab. Try to use Colab to get used to Python or get started with Python. So today we'll have a quick look at multi-class logistic regression example, which is in the repository that which is in the repository, which also has the syllabus page, for example. But anyway, I will link it. I'll show the link today and when we get there. And we'll see basically that multi-class logic regression is, has its own limitations, and therefore we should study the next thing, which is, some very basic type of neural networks, which are feed-forward neural networks. And then, so let me not explain all the goals. Let me at least tell a couple of goals, which I'm hoping to cover today. First is, of course, when I show you some code base, I will spend some time trying to get a sense of get some sense of Python, and also the different steps, different parts of the code. It's a small script, so we'll try to get a sense of it. And then what we'll try to spend time on is to understand feed-forward neural networks, or their architecture, or their specification, in a clear way. So in particular, there's going to be some emphasis on some terminology. So there's a notion of layers, and some layers will be hidden, and so on. And there's also this notion of nonlinearity. Okay, and in particular, these models are nonlinear. For example, logistic regression, or SVM, that you've seen before, are or at least without the kernel trick, are considered linear models. Okay, and including linear regression, for example. So we'll look at nonlinearity and how it comes into the picture for this class of feed-forward neural network models. Okay? And if time permits, we're going to look at convolutional neural networks and some details related to them. And I can get to these goals when we get there. Okay. Um, okay. So yeah. So what we'll start with is backpropagation. So um, this is also is basically an instantiation of chain rule. Okay. So what does chain rule mean? So let's say we have a function. This is just an example before we even get into other examples that I have, small examples. So let's say my, some output, okay, some variable or some value is equal to uh, 3 plus uh, x squared divided by um, 2x plus 1. Let's say this is a um, function, right? It's given any value. So this is a function, right? So I can define it as a function in Python. Define f, given x, you can just return. You can do all these operations. 3 plus power, like, I think star 2. Um, so there's some way you can specify it. Let's not worry about it. So this is just a function, right? Now chain rule just means, okay, let me say, hey, why can't I say y is equal to um, um, yeah. So why can't we say y is equal to 3 by, let's say, 2 plus x plus x squared by 2 plus x, sorry, 2x plus 1. I just split the numerator. Let me call this intermediate output. Let's say it's called z1 plus z2. So where z1 is just 3 by 2 plus x, and z2 is x squared divided by 2x plus 1. Okay, so okay. So once I do this, now I know z1 is just 3 by 2x plus 1. Okay. So what I can do is now say, hey, what is the rate of change of z1 with respect to x? Okay. So there'll be some value here. Okay. This, whatever be the value, let's not compute it now. Now, I know that I also, for just looking at, I know that y, since y is equal to z1 plus z2, dy by dz1 is equal to this. By the way, dy by dz1 is just the derivative of y with respect to z1, is equal to, in this case, it's equal to 1. But you can just look at, hey, how does if I change z1 by 1 unit, how much does y vary? Keeping everything else constant, you can see that, hey, if I increase z1 from whatever value it is, let's say 1 units to 2 units, y is also going to change from 1 unit to 2 units. Therefore, rate of change is 1. So I know this, how y changes with z1. Let's say I also compute how z1 changes with x. Then I can stitch these two. I can use these two together to say how y changes with respect to x. Okay. So although here it's just a simple sorry, here it's a simple numerator with denominator, you can actually compute them, and that's what you might have done in calculus classes. But we don't have to worry about how to do that in with pen and paper. But chain rule is just that you can find dy by dx is actually equal to dy by the z1 times the z1 divided by the sorry the x plus dy by the z2 times the z2 divided by dx. Okay. So all I'm saying is this partial derivative seemed messy, like some input to some output, maybe a complicated function, a complicated transformation going on, right? From here, if I set a value x, to get to a value of y, to find its change, find the rate of change of output with respect to input, you can, for example, introduce these intermediate variables and say, hey, the rate of change is actually the rate of change of the output with respect to some intermediate value times the rate of change of the intermediate value with respect to input, for example. Okay, and because there was z1 and z2, I split it out this way. Okay, and in this example, it just turns out this part, the first is equal to 1, and second one is also equal to 1. Okay? Because y was just equal to z1 plus z2. And then you can just focus on what is the rate of change of the first term with respect to x, the rate of change of a second term with respect to x, and that should be very clear, right? Since y is just a sum of two things, if I find the rate of change of the first term with respect to x and the rate of change of second term with respect to x, and add them together, they will give me the total rate of change of y with respect to x. Okay, that's what chain rule is. And just to use, let's say three again, instead of explicitly talking about that function, let's say y is some function of x, but in the previous example, I wrote some numerator divided by denominator. So instead of that, let's say y is equal to some function g of z, and let's say z is equal to some function, let's call it g1, some function of x. Okay, so let's say it's like this. So basically y is a function of x, but the function of x can be split into two functions, g1 of z, and then z itself as g2 of x. So basically y was equal to g1 of g2 of x, right? So now rate of change of y with respect to x is, you can, since you know that, I mean, since I wrote it above, you can write, okay, let me change y with respect to z. Okay, and change z with respect to x. Okay. And if you really want to, forget about all the actual details about these symbols, rate of change of c with respect to x, which has some formal meaning in a subfield of mathematics. Here you can just see that, hey, these two terms appear in numerator and denominator. They kind of roughly cancel out informally. So if you want to find the rate of change of y with respect to some input, you can always introduce some intermediate variables. Okay. So we'll make this more precise. So chain rule, this is an example of a chain rule. Chain rule just means, you have a chain of such multiplying factors. Okay. And we'll look at a precise example right after this general slide. Actually, let's look at the example first and then come to that general slide. So here's an example. Instead of y and x's and z's, here the inputs are a, b, and c. So a and b and c are just stand-ins, just placeholders for some numbers that I want to plug in for a, b, and c. And G is a generic symbol that I'm using to say, hey, this is a function of A, B, and C, and the function explicitly is A times B plus C. Okay, so I mean this is it's a very simple function, right? It takes three arguments, multiplies the first two, and then adds the third, right? Now, to we saw chain rule. So at this point, forget about this computational graph and this second bullet point here. At this point, I can directly say, hey, I know G of A, B, and C is equal to A times B plus C, okay, for whatever three numbers. Then I know how to find the partial derivative of, so now I'm going to use slightly different notation, partial derivative of G with respect to C, for example. I know this function, so I know this should be equal to 1, because if C is only appearing in the second term, and if I change vary C by, let's say, 1 unit, the output, the output, which is G function, only varies by 1 unit, right? So this is called partial derivative because I'm holding A and B fixed. Okay, I'm saying how would output change when, let's say, a part of the input changes, and that's why the notation is this partial symbol. Okay, um, so given this function, I can already find all sorts of so this is generally like y, right? So given I can find the partial derivative output with respect to C, I can also find the partial derivative with respect to output with respect to A, right? So partial derivative with respect to A is second term doesn't involve A, so it doesn't, it's a constant, so it doesn't change, so it's zero basically. First term, you can see that it's it varies with A. So if I increase A by 1 unit, let's say the output changes by B units. Okay, and similarly, partial derivative of G with respect to B is equal to A. Okay, so without knowing anything about uh, backpropagation stuff, you just given a function, you can, if it's a simple enough function, you can find the partial derivatives of outputs with respect to inputs. Okay, but the story is not easy the moment the functions become more involved. Okay, so and that's where we can offload that task of, hey, how do you find derivatives of outputs with respect to inputs um, um, uh, for more complicated functions. And in particular, we're going to talk about, later on throughout this course, we're going to look at a lot of deep neural networks. They all do something, right? So all classifiers do something from input to output, right? Given a bunch of parameters. And if you recall the optimization component last time in the review, I said in the optimization part, we can make use of gradients, okay, and gradients to update the parameters of my model so as to, let's say, minimize my loss and so on. So those gradient objects are what can be computed using chain rule and therefore backpropagation. Okay? So before I tie back the story of, so what we've done is zoom into a specific underlying technique that's needed to come back one step later, a few minutes later, to say, hey, now I know how to compute gradients for anything, and these gradients are used for optimization of any parametric model, in particular neural networks. Okay? So we'll connect that story back a few minutes later, but let's focus on uh, trying to represent this function in terms of like a graph, which is going to be called a computational graph, and then identify some simple rules for doing this, for computing this chain rule, okay, for implementing this chain rule, and that's basically is called backpropagation. So let's come back here. So this function I can represent using a graph. Okay, and what is a graph? A graph is a collection of nodes. Like these are nodes, and these are called edges. Okay, this doesn't have to be like so they can be just like straight lines here. This is just one way to draw a graph. So a graph is nothing but a collection of nodes and edges. So given any function, typically given any function in our modeling setup, they're generally a bunch of numbers, right? A feature vector is a number. It will eventually get transformed to a score vector, for example, right? Or some prediction probability of let's say spam, no spam, or something like that. So it's all numbers numbers are input, and eventually a number is an output, right? So and these numbers are basically what types of operations would happen. Typically, there's going to be additions, multiplication, divisions, or some simple like exponentiation or application of like a sine or a sine function or some simple transformation like that, right? So these nodes are going to correspond to those transformations or those simple functions. So you can see here for this function, I have used a node to represent the multiplication operation and a node to represent the addition operation, right? Um, and you can see I've plugged in two inputs to the first node, plugged two inputs to the second node, and this is the output. This is that D of A, B, and C. Okay, so this is an example of a computation graph, and we are just looking at one example here. You're not, we're not going to do manually try to figure out what's the computational graph of any arbitrary function, or for example a neural network, or any, let's say, logical regression model or something like that. But it's good to know what's happening behind the scenes, and once we have this graphical representation of a function, we can really think about, hey, backpropagation or chain rule can be done somewhat mechanically, and that's what I want to show next. So is the graph representation clear? Does anybody have a question? Okay, so I'm going a little bit slow. So if this is if everybody understands and knows this, then do let me know and I can speed up a little bit. Okay. I don't want to err on the side of speeding up too much and speeding up and then some people falling off. So I apologize to folks who already kind of know some of these ideas. Okay, especially if you folks who already know chain rule, this will just be a recap. So here's how. So here's BackProp example. So previous example was just, hey, here's the function, here's the graph for that function. Let me start with an even simpler function. Let's say, sorry, let me start with the same function. Now we're going to do BackProp. So BackProp is just implementation chain rule. So what do we want at the end of the day is just the gradient of G with respect to A, gradient of G with respect to B, and gradient of G with respect to C. But I just showed you a couple of minutes ago what the gradients were. They were just, we just saw what the gradients were. It was just this value, this value, and this value. And even this, you don't have to memorize. I mean, there are a bunch of rules that you can look up on in an undergraduate calculus book or something like that, and actually mechanically figure these things out. But let's come back to this example. So what does the graph give us? The graph is going to help us get these gradients in a mechanical way, and this way for this example is somewhat easy, but the same ideas apply for even much more complicated functions. So what we do is a trick, is a rule which is as follows. So for any node, so we'll focus on one node. So let's say focus on this node. What we'll do is there's an so each node or each of these nodes, as I said, is a small unit of computation. It takes some inputs and produces some outputs. So what we'll do is locally try to locally compute a part of the chain rule, which means that we'll start. For example, what I'm showing is with this arrow is that we'll start from the output all the way to the output. So this graph has some directionality, right? I know that this edge should ideally be the output of this whole function that I'm computing. So we'll start from the last um, edge, okay? And there's this notion of last edge because this graph, if you notice, is actually directed, okay? So this edges have this arrows, if you see this, okay? So this graph is directed. It also is acyclic. Acyclic just means that there is no like a closed connection between nodes. So an example of a cyclic graph would be, here's an edge um, from some node, here's another node, and then maybe I'll also go some other node. But then I come back to the original node. If there is a directed graph like this is directed graph, certainly, with some 3 nodes and 3 edges, right? But this is a cyclic graph, and we're not going to talk about cyclic graphs. Most functions are generally acyclic. Okay, and therefore that's why I can pick a last. Let's talk about the last edge of the last node because that's the function output basically, and we're going to do backwards, some sort of backwards local computation. And that's where back propagation comes. So you do some computation all the way to end, propagate it back to your basically parents, or in some sense some part, earlier part of the graph, and then do some local computation there and pass on the whatever computation you're doing to earlier parts of the graph. Okay, earlier parts of the graph, just call them parents. Okay, and later parts of the graph, call them children. And that's, in fact, that's the terminology used in that branch of um, study. Okay. So what we do, and the trick for any node, is that there's always going to be an incoming gradient. Remember, what this information or whatever we pass on from, let's say, this node to its predecessor nodes, that information is just about gradients. Okay, we ultimately, at the end of the day, we just want the gradient of the output with respect to some pre-specified input. Okay? So there's going to be an incoming gradient, and there's going to be some uh, local gradients. Okay, so there's going to be incoming gradient and there's going to be local gradients. And what you do is pass on some gradient information to your predecessor nodes. Okay, so that's the general idea here. So let me actually step back for 2 slides and show that same idea here. So this is a general representation. So here, this function, for example, could be just as simple as a plus b. Okay. What I'm trying to say is that in once you have a graph representation for a function, then computing gradients can be done by parts, by zooming into one node at a time. Once you have graph, you'll have a bunch of nodes. You can zoom into each node and think of just the local computation which aids computing your original goal, which was the gradient computation, right? So what do I mean by that? Just if you look at this figure, there's some incoming gradient. Okay, there's some local gradients. Okay, local gradients are nothing but, because I know this function, this node is that local function h. It could be a plus b. I know the local gradient, which just means that I know this function's output, this node's output with respect to its input. If it's a plus b, I know that gradient of h with respect to a is equal to 1. And similarly, gradient of h with respect to b is equal to 1. So these are called local gradient values, and I can compute them because I don't need to know the rest of the graph to just compute my own local values. Okay, gradient of the function with respect to my input, I can just compute, sorry, gradient of myself with respect to my input, I can just compute that, right? So these two, I know these are local gradients. There'll be some incoming gradient. Somebody else, maybe there's a node which is further ahead, to me downstream, that computes some gradient. Okay, sorry, that sends me some gradient. Okay, I don't have to even think about, it just sends me some gradient. Let's call it gradient of g with respect to h. Okay, h is just this node's output. So generally, whatever the downstream, if there's a node here, h goes in, and then this is, let's say, g, h goes in here, and there's some, let's say, 1 by h or something, some computation there. So what, this node will pass on to its predecessor. So this is the predecessor, and this is, let's say, this is the downstream node. It will pass on a incoming gradient. Okay, this is what I meant by incoming gradient. Okay, it's just, I just need to be in the denominator. If I'm the h node, I just need to be in the denominator here. And given this incoming gradient and the local gradient, I can compute gradients or partial derivatives that I can pass on to my predecessors. So in this blue note example, it's going to pass on its local gradient times the incoming gradient, and its local gradient times the incoming gradient. Okay, in each of these edges. Okay, to whatever node connects to it. Okay. So that's it. That's backpropagation. So instead of looking at the whole graph, every node, if you just zoom in onto that node, it just has to get some gradient from its output. Like not output, but this edge. Let's say it's a two input, one output function. It's getting something from its output edge, multiplying that number. So remember, all these gradients are just, for simplicity, you can just think of that as one number. Okay, like a one-dimensional number, or it's not a vector, but it's just a single number, scalar. You get a number from your output edge, multiply it with the local number that you've computed, okay, and just pass it back to that edge. Okay, so because the local gradient is with respect to a, you pass this together onto this edge corresponding to a. If it is connected to some previous node, that will receive that number. Okay, so that's the back propagation in a nutshell. If you can do this, whatever I'm showing in this slide, at every node in a certain way, since it says back propagation, you start from the last node and then keep moving backward. And if you do that, you are essentially doing what I showed 2 slides ago, which is so what I showed here, which is this. Okay, you're just implementing chain rule. If you do what I just said here at each node, you are just implementing chain rule. Okay, and we'll look at that through this example here. So um, yeah. So let's look at this example, this function. If you recall, this was g is equal to a times b plus c. Okay, and we are just calling a times b as h, and that's the sorry, yeah, a times b as h, and that's the intermediate node. So if you look at the second node, g, this is a g node, and this is a h node. Okay, so g node takes 2 inputs, h and c, outputs h plus c. Okay, so clearly I know its local gradient g with respect to its any of its inputs is 1, and just as a initialization, you can just think of the last edge incoming gradient is always equal to 1. Okay, gradient of g with respect to itself is equal to 1. So if you start with 1 and local gradient is 1, if you multiply those two, whatever gradient I need to pass here is also equal to 1, and whatever gradient I need to pass here is also equal to 1. Okay, so gradient of g with respect to c is equal to 1. That's one of the answers. We already have it. Now I passed 1 back. Now gradient of h with respect to itself, it's one of these arguments. Let's say a is equal to b, and gradient of h with respect to its second argument b is equal to a. So the local gradient is equal to b for the top edge. So the gradient I need to pass is equal to b times h here. Okay. And the gradient I need to pass back, if there is previous nodes, is just a times a times the incoming gradient, which is equal to 1. Okay, and it's of b times 1. Okay. Now you can say, hey, there's no node anymore. So what are you passing here? This, if there's no more node, then whatever I pass here is equal to the gradient of the output with respect to the input. Okay, so you can just call a as the input, and therefore a gradient of the output g with respect to a is equal to b times 1, which is equal to b. Okay, and that's exactly what we thought. Even looking at all this, we could just eyeball, right? So we just said gradient of um, g with respect to a is equal to b. So and that's exactly what we did. So here, um, yeah. So any questions about this small BackProp example? So just think of, if you're getting confused, just think of, hey, what do I know about chain rule, and how does if you and how does BackProp deal with chain rule by just doing local computations, local multiplications of the chain rule terms, right? In chain rule, there's always going to be a gradient of g with respect to some h, and h, gradient of h with respect to, let's say, a. Chain rule is just about multiplying those two to get the gradient of g with respect to a. That is just basically being translated into this in terms of graph notation, and in terms of this incoming gradient times the local gradient multiplication idea. Okay. And that's part propagation. um,
Professor, I have a question. Just to clarify, that the local gradient is generated in each of the nodes. Am I right?
yes, yes. Yeah, there's always going to be every node will know some information about it itself. Forget about the rest of the graph, and that information is basically, hey, how does my local node's output change with respect to my input? For simple functions like multiplier and addition, you know the answer, right? For addition, it's just gradient is equal to 1 for with respect to any of my inputs, for example. Yeah.
Okay, and one more question is, if suppose here the incoming gradient for the last node is 1,
Mhm.
and also for the multiplication node over there is also 1, is that right?
Yes, exactly. So yeah, so for the first circle, let's focus on let's say this circle here with the star mark.
Okay.
So for any graph, we'll by default take the last thing to be always 1. Okay, the local gradient of g with respect to g by definition is equal to 1, and then incoming gradient here is 1, local gradient is 1. Therefore, the gradient that needs to be passed on to its predecessor or its parent is equal to 1. Okay, 1 times this, 1 times this one, these two.
Okay.
Yeah.
And could you please give us an example where it's not 1, or is the example
Yes.
coming in the next?
Yes. Yes,
line.
yes, 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 yeah,
Okay.
yeah. In example two, we're going to look at a slightly more involved function. But the idea is the same. So what I want to get from first example is that, hey, let's not, whatever be the function, okay, it may be even much more messier. And I think the first time I wrote some function, there was some numerator and denominator and squares and stuff like that. At the end of the day, all that can be broken down into a bunch of additions and multiplications. And so you can draw that as a graph. Okay, so just as an exercise, let's go back to that function before I get to example two. There was this function that I wrote, right? So this can be actually drawn as a graph. Okay, it's input is x, right? X goes to one node, which squares it. Okay, uh, this becomes x squared, and there's another node here which adds 3 to it, so this becomes x squared plus 3, right? Yeah.
Oh,
And then this on the second side, the same x goes to another node. Okay, this is all directed here.
yes.
Sorry, I should draw it properly. Yeah, goes here, and then gets multiplied by, let's say, 2. You don't even have to separately write 2 here. You can just say this function itself produces 2x,
Okay.
and then there's an addition. I guess, yeah, addition here. This is 2x plus 1, and then these two. This is a division function. So whatever is the two inputs, this local function, sorry, is just going to produce, whatever. Like if this was, yeah,
X squared plus 3
yeah,
by
a by
2.
b, and whatever is the input. Let's say this is called a, this is called b. Whatever is the, this is the output. Okay. So you can write it, 3 plus x squared divided by 2x plus 1. So this is the graph. Okay. And you can really do backpropagation just the same way I said. So if you just want to find y with respect to x, there are these paths. You just have to find the local gradients. And computer actually does it this way. Okay. And that's why I'm trying to explain. This is not black magic, and this is how you would compute gradients.
Okay, this is actually new to me. I know the chain rule, but this is new to me. So yeah.
Yeah, this is just a representation of the chain rule, and so that the computers, they don't have to remember all the chain rule. Memorize all the rules, right? Like typically, the way you would do it in calculus is you remember, hey, gradient of log x is equal to 1 by x with respect to its input, or gradient of 2x square is
2x.
2x, and so on. So there's a bunch of things that you'll remember, and then what you'll do is, and you'll also remember some more sophisticated rules like gradient of um, let's say, uh, u by v with respect to v. Okay, no, not this way. I didn't
Minus
want to write this way.
u.
But anyway,
u bar.
I'm just trying to say that there are more sophisticated rules, right? Let me
Yeah.
not write the product rule or things like that right now.
Yeah.
Don't want to
Got
confuse people. Yeah. So let's actually come back to the second example. It's a little bit more involved, but it's I think it's good to go look at it, because at the end of the day, this is what computers do, and we'll actually be doing just scratching the surface, just so get a sense of, um, um, for example, these packages that I have mentioned maybe in the assignment, as well as we'll kind of use these packages throughout this course. One of the packages is called PyTorch. It's quite famous, where there's a lot of implementations by a lot of researchers on different types of neural networks. But the behind the scenes, PyTorch is basically just doing, so one of the key features that PyTorch implements in a very robust way is backpropagation. Okay. Um, so it's good to get a sense of how it actually does behind the scenes. Okay, so in fact, behind the scenes, it just represents any function, any model, any input output type of function as a graph, and just does these local computations and because these graphs are directed and acyclic, it's not there's no ambiguity. Okay. So let's look at this function. It's a little bit more complicated function, 1 by 1 plus e to the power minus ax plus by. Okay. So if you forget about all this graphs idea, and if I give you this function and say, hey, can you tell me the gradient of g with respect to x? You can find it. Okay. You can do basically apply chain rule and all your ideas about all the tricks that you might have memorized to work with this directly. But here we'll try to see if we can apply what we saw earlier. Okay, let's draw a graph, and in fact, you'll see that the graph has nodes with varying degrees of node complexity. For example, here's a graph in the red box. The first node is just a multiplication. So I'm just saying that, hey, let me call a times x as an intermediate output c. I also call b times y as an intermediate output d. Remember, there's an a times x here and a b times y here. Okay, so in particular, what I'm saying is g is equal to 1 by 1 plus e to the power c plus d. Essentially, that's what I said. So where c is equal to a times x, that's this part, and d is equal to b times y. Okay. Once I have c and d, let me even make it simpler. So there's a minus here. And let me call this function actually equal to 1 by 1 plus e to the power minus z. Okay, where z is a simple node which just takes c and d as inputs and produces c plus d. Okay. And then now this node, I just left it as a much more, I guess, complicated node where it's doing this whole operation 1 by 1 plus e to the power minus z. So if z is an input and you want to produce output, the node is just computing this. Like take the z, negate it, exponentiate it, add plus one, and then invert the whole thing. Okay, so it's a bunch of things. But you can consider that as a also a node if you want. Okay, and in fact, this is your first I guess exposure, and some of you might have already seen this. This is called a logistic function, and we'll see it again in maybe half an hour or 15 minutes. We'll talk about nonlinearities. Okay, it's a sigmoid function or the logistic function, they're all the same name. Or also maybe if you've done generalized linear models before, it's also an example of a link function. Okay. But anyway, so those are all side details. So let's come back here. So this is, let's say this is the graph. Okay, we can further break this, by the way, but we are not going to do that for this example. So now let's do backpropagation. And this time, what we'll do is we'll also say, hey, I don't want the gradient of output with respect to input in a general expression. I want it at a specific value, okay, where, for example, gradients are supposed to be, you know, could be sensitive to the location where you're asking for the gradient. Let's say, let's think of a parabola, right? I think this was the example I used last time. So this is, I think, yeah, that's okay. If you really want to know, so this is like x minus, let's say 10 square plus 2. Let's say this is 0, 2, and this is 10, 0. This is a parabola. This is a square function. What I want to say is that the gradient of output, let's say y is equal to this function. Okay. This whole thing is, this is the function. Gradient at this point of x, let's say x is equal to 20, is dependent on the value of x. Okay, so the gradient is not constant. What I'm trying to say is that so for example, the gradient at 10 equal to 0. Okay, so okay, let's look at this. So you can see, since let's not worry about chain rule right now. So the gradient of y with respect to x is equal to what? So it's 2 times x minus 10. Okay, just like we saw, gradient of x square with respect to input is just 2x. So this is fine. This, I hope everybody's comfortable with. If not, it's just memorize this. It's fine. It's not needed for us. So you can see that gradient of y with respect to x depends on x. Okay, so when I ask for a gradient, people sometimes write this notation. They'll put a vertical line here and say, hey, tell me what is the gradient at x is equal to whatever. Maybe if it's maybe 10. When it's 10, it's actually equal to 0. And when it's, let's say, 20, it's actually equal to 20 minus 10 times 2, which is 20, right? So you generally ask gradient at a given input value. Okay, and that's what I wanted to say. Here, I'm not asking for a general gradient, general mathematical formula. I'm just saying, hey, I know what the inputs are. I'll tell you what the inputs are: a, b, x, and y. Now, just tell me what's the gradient of the output with respect to input, let's say a, when these are the values of my input. Okay, so that's just one minor detail. So before we get to gradients, let's see what the function evaluation itself is. So a times x. So a is 2, x is minus 3, so it's minus 6, a times x. So that's what's written in the back brackets here. Similarly, d, which is equal to b times y, is 4, right? And then z is the sum of these two, which is equal to minus 2 here. And then 1 by 1 plus e to the power minus z is 1 by 1 plus e to the power 2. Okay, that's the output. So for this input, the functions are, like this, what you would call a forward pass. Okay, it's called a forward pass. Okay? Because it's forward in the sense that you have this graph, and since it's acyclic and directed, we can think of left to right type of interpretation. Oh, left side are inputs, they kind of forward, they flow through this graph, and you get this output, which is 1 by 1 plus e to the power 2. Okay, so that's the forward pass. um, for these input values. And now the question is, hey, can you give the gradients of the output with respect to with respect to maybe all of these four inputs at this given value of the input. Okay, a is equal to, b is equal to 1, x is equal to -3, and so on. So that's the question. So is the question clear? So I just want to find gradient of g, for example, with respect to uh, a, given I already given a is equal to something, b is equal to something, c is equal to something, d sorry, I should have written x, a is equal to something, b is equal to something, and x is equal to some value, and y is equal to some value. There are some four values here. I mean, the values are written there. I didn't want to repeat it. A is equal to 2, b is equal to 1, x is equal to -3, and so on. Okay. So just tell me the gradient of this. So how do I find this gradient? And similarly, not just A, can you tell me the gradient of G with respect to B, and so on? Okay. So I see somebody has raised hand. Do you still have a question? Okay. It looks like no question at the moment. But do interrupt me if you have questions at any point of time.
Sure, Professor. Thank you.
Mhm. Okay. So now let's do that backprop where I said, hey, let's not worry about all these nodes. There looks like 4 nodes here. Let's focus on one node. Okay, just let's focus on the one node. And I wanted to, so I can't get rid of the plus node here. Let's focus on just this node. Okay, the 1 by 1 plus e to the power minus c. Okay, so that guy, the input gradient is 1. Okay, I mean, the gradient of g with respect to itself is equal to 1. Now, what is the local gradient? It only has one input. So the question is, what is the gradient of z with respect to z? Okay, and you can see that this g function as a function of z was equal to 1 by 1 plus e to the power minus z. Now this guy, I left it the node like this, but we'll have to derive this gradient at, let's say, z is equal to what is the value? -2. Okay. So sorry, I should not zoom out. So I know G is this, right? And I want to find this, right? So let's just apply what we know about chain rule. Okay. I'm wondering if I should do that computation, or is it? It's not really illustrative. So okay, let me not do that computation. Okay, so this computation of gradient of G with respect to Z, you can, we can actually compute it, okay, analytically. So now there's no help of a graph or anything like that. You can certainly break this down into its own graph, and if you can do chain rule, or you can just apply chain rule here. But it turns out that the local gradient of G with respect to Z is just this. Okay, so it's e squared divided by 1 plus e squared the whole square. Okay, so why is, and this is actually exactly evaluated at z is equal to 2. Okay, z is equal to -2, sorry. So let's take this as a input, because so let's take this as given, because I don't want to spend 5 minutes just trying to find the derivative here, which eventually just evaluates this. Okay, let's say we have we have the local gradient. I know the incoming gradient is 1, local gradient is this. Therefore, the gradient, the red arrow that I need to pass back to the previous predecessor node, the plus node, is just incoming gradient times local gradient. Okay, and since incoming gradient is just 1, so what I need to pass back is just this e square divided by 1 plus e square the whole square. Okay. So it doesn't matter some complicated expression, but it's just some gradient that I'm passing back to my previous node. So let's focus on now the previous node, the addition node. I know that for addition node, the local gradients with respect to either of its inputs are just 1. Like, gradient of z with respect to c is 1. Gradient of z with respect to d is also 1. So the local gradient times the incoming gradient, which is this underlying thing. I keep underlining it a lot more, but is what I'll pass back to, for example, on the C edge. And similarly, the same thing I'll pass back on the T edge as well. Okay, but let's focus on C edge because now we have two things. Let's only focus on this direction for now. So is these two steps clear? So first we just took an incoming gradient, found the local gradient, multiplied them together, and send it back. That's what we're doing. Okay, so this red arrow, as I was saying, is basically captured by this square box here. Okay? It's just the um, local gradient of z with respect to c, which is equal to 1, times the incoming gradient, which was whatever it was, whatever the previous thing was. Okay? Now let's go one step and just focus on this multiplier node, where I know what the incoming gradient is. Incoming gradient is given by this um, uh, square box, right? So let's focus on that. Uh, so gradient of, oops, sorry, I think I already did that here. Um, Okay, what we're doing here is actually not going just on that direction. We're actually also computing the local gradient with respect to, so the local gradient that we pass on to step D here. So sorry, the multiplier node on the edge D here, and this local gradient and this local gradient, these two incoming gradients to the predecessor nodes are the same. Okay, so there's no need to I guess um, um, get discuss in more further. It's basically the gradient of uh, uh, g with respect to d is the same as the gradient of g with respect to c. Okay, those are the two increment gradients to these two multipliers. Okay? So forget about the rest of the whole figure. If you just focus on this part, which I've highlighted and which I've partitioned, on that, there's an incoming gradient, which is this guy. And this guy on the bottom multiplier node, there's an incoming gradient, and that's this guy. Okay, that's it. So let's not worry about the previous computations that have happened because it's all about locality with backpropagation. Now, multiplier, we know what the local gradients are. Gradient of c with respect to a is equal to x, and similarly, gradient of c with respect to x is equal to a, right? That is you know uh, those two are known facts. So with because I know the local gradient, the gradient of from right there, we can say, hey, the gradient of g with respect to a is equal to gradient of g with respect to c times gradient of c with respect to a. Okay, so this part is what I said. This is equal to x, and this is the incoming gradient. Okay, and this is we know is equal to e squared divided by 1 plus e squared the whole square. And we also know x value is -3. So -3 times this is exactly the gradient of g with respect to a at this given input. Okay. So, and similarly, we can do the same step for x, for b, and for y. I think yeah, I did it for the last, only for the last, so only for y. And for y, we can again recap. So I know the incoming gradient to d. I know the gradient of d with respect to y. It's actually equal to b. And hence the gradient of, so that is what, so this is the local gradient. And I know what the incoming gradient is. This is the incoming gradient. And therefore, the gradient of g, the full output here with respect to input y is equal to uh, this, and this is because b is actually equal to 1. So it's actually b times whatever is the incoming gradient, and b is equal to 1. So is that a little bit clear, or was it unclear? If you have any questions, do ask. But basically, if you even if you don't follow this a little bit, this a little bit cluttered diagram here, just go back to the original idea. The original idea is you have a function. If you can represent it as a computational graph, as I said, this is a computational graph, then you can just focus on some incoming gradient times the local gradient. and pass it back to your predecessors. And if you can do that for every node, then you pretty much know the gradient of the final output with respect to the initial input. Okay, so you can, that's, this is the final output and this is the initial input, and we can compute those things by just doing some localized operations at every node on the path. Okay, so the nodes on the path from G to A are this node, this node, and this node. So as long as we can do that local computations at each node, we can find a gradient. And if you actually see what all you're multiplying. So there's a local gradient times local, there's an incoming gradient times local gradient times local gradient times local gradient. It's just chain rule. Okay, so it's just a multiplication of a bunch of local gradients, and that's what chain rule is. And this process is just called backpropagation. Now let's actually give some extra details here. I think this is not critical for us at the moment. And neither are these texts. Okay, so what I'll do, by the way, in many of these modules, many of these lecture notes, is skip those slides which are not the core points. They're certainly useful if and we can revisit them during office hours or if I have time later. But yeah, what I wanted to focus on is not the details of how a functions, how a function which can, how does a code, how does, like, let's say PyTorch code look like? That's not what I want to get to now. I want to now tie it back to our original component of why are we looking at backpropagation, right? So I want to tie it back to that. And in particular, I want to tie it back to gradient based optimization that we briefly discussed last time. Okay. So last time we said if we have weights, so yeah, if we have W, so last time I think we had W and B. So I said, hey, W1 and B1, let's say one represents like the new values. Let's say I started with old values, W0 and the old values. Then what I would do is take the old value, subtract. Generally, if you are minimizing a loss function, you would do a subtraction. This is called gradient descent. So descent means subtraction, ascent means generally addition. Okay. So by the way, those are just, they're not like hard coded rules. The interpretation really comes from uh, uh, like this. You can interpret why there has to be a negative sign to actually make updates and to get to the bottom of the loss function, for example. That's what we want to do generally in when finding the best classifier. We want to minimize the loss function. If you're trying to minimize, you need to go in the negative direction of the gradient. Okay, so um, so W naught minus some learning rate, and I said this is just a constant. So generally, I don't even want to write alpha. Let's say 0.1 times the gradient of the loss with respect to W. Okay, and the gradient of loss with respect to W at W is equal to W naught, which means that if the gradient happens to be still a function of W, they just substitute the value of W naught there, because depending on where the W naught is, maybe the gradient is high or low. We just talked about the parabolic, the squared example to just say that, hey, gradient depends on where you're evaluating it, right? Similarly, for B also it will be something like this: 0.1 times gradient of loss with respect to B, evaluated at whatever the B value was. Okay, so this is essentially the core of many optimization schemes that you can employ for training neural network models. Okay. By training, I just mean your data is anyway given. You want to get to a minimal loss value. You want to really update the parameters again and again and again in an iterative fashion. So you can run this in a for loop. Okay. So you want to update these weights. So for example, here I've just written two parameters because we had this type of an example last time, two sets of parameters. But you keep updating them by applying this type of a update rule. Okay, so whatever the previous value, subtract something from it. And to subtract something from it, you need to know the gradient. So what is the gradient of the final output with respect to an input? Here, the input happens to be the parameter, the current parameter. Okay, I want to find so data set is fixed. I just want to say, hey, I have some current parameters, W naught, P naught. Can you tell me how does the loss function move around it? Okay, how much does it vary? If I change the parameter by 1 unit, does loss function go up and down? That's what a gradient is, right? So once I can get a handle on these two gradients, I can actually go to a new candidate parameter value. Okay. And one of the assignment questions really asks you to do this for a simple, I think, 1 or 2 dimensional problem. So you'll get a sense of that this update, this update rule actually works roughly. And as I said earlier, it's a core for a little bit more sophisticated algorithms that are actually used to train all the state-of-the-art neural network models out there. Okay? There are many different variations to this basic idea, okay? Including a lot more rigorous way of finding out what should be, oh, hey, this should be 0.1, should it be something else, or should this number be changing as I do this for loop again and again, and things like that. Okay, we are not worried about that at this point. So this is, as I said, is gradient descent. And the connection to backprop is that you want to apply backprop through some underlying package to be able to compute this guy as well as this guy. Okay. So now let's come back to backprop and an extra adjective, a version of gradient descent called batch gradient descent. And so this slide, I just want to introduce the notion of batch, uh, which is uh, which is a little bit which is basically a special case of this thing in a square box. In the square box, we are doing gradient descent. But what does batch gradient descent mean? Batch gradient descent is something that we specialize when we are trying to minimize our classifier loss function. Okay, remember we had that thing, um, toss entropy loss function that we saw, or the logistic loss function that we saw last lecture. So some loss function. Generally, as I said last time, we saw the loss function is a function of both the data part as well as the regularizer part. In particular, the L data part is a function of, if you recall, L was equal to L data plus regularizer, something like lambda times, something like norm of W square or something like that. And L data was equal to L1 plus L2 plus, if I have 1,000 examples, it was L 1,000, right? Uh, so batched gradient descent just means, hey, I don't want to get the gradient of gradient of L with respect to your current parameter, or with respect to parameter. I want the gradient of, what I'll do is every iteration. So every iteration just means when I do this for loop, there is going to be every time, let's say, print statement or something like that, right? Not print statement, but this update. Uh, so whenever I do that update, I'm gonna do a batch. So I'm gonna pick, okay, hey, I'll only consider L1 to L1, L2, L10. I'm only gonna look at L1, L2, L10, L1, L2, sorry, L1 plus L2 plus, let's say, L10. I'm only going to consider this to be representing my data. Okay, so that's a batch. So this first, second, and 10 up to 10th examples are a batch. Maybe in the next iteration, hey, I don't want to look at the first, second, third, up to 10th examples. Let my batch be equal to 11th to 20th examples only. Okay, then I'll only compute the gradient of L1 with respect to W. Sorry, delta. Gradient of L2 with respect to W, and gradient of L10 with respect to W. Okay, so um, in each uh, round, in each round of this gradient descent update rule, where we are updating parameters, right? We will do the following. We'll choose a mini batch, or a batch. Batch is, just think of it as a collection of observations in my data. If I have 1,000 observations, let's say my batch is, hey, take only the first 10 observations. Okay, that's a batch. Okay, so let's say this will be 10. So I'll take 10 observations only. Then what I'll do is, remember now the graph idea. I had this 10 observations. Given W and B, and given these 10 observations, I'll compute the L data. And similarly, I'll use W and B to also compute regularizer, and together it will give me L. And so I'll not use the full data in this batch in this forward propagation. Okay, this in this graph idea, right? Forward propagation. Then what I'll do is I'll only compute. Now I'll do back propagation, okay, to get the gradient of L with respect to W. But since I only use 10 observations, it's not the actual gradient of the full loss function, right? The full loss function should ideally have all the 1,000 observations, but it's only going to have 10 observations. So that's fine. Whatever be this number, whatever be this gradient B, it's going to be some number or a vector, typically a vector, because parameters generally, vectors. or even matrices. So this can also be a matrix. This has in this gradient, and then I'll just use that in this update rule, okay, in the for loop, and then keep doing that. Uh, uh, so do that update, and the next time I may choose a different batch. Okay. Any questions about this idea of gradient descent we saw last time? Crudely, I mean, this is just what we saw last time was um, what we saw last time was what is there in this box. The batch, this notion of a batch, all it's saying is, hey, don't find the gradient with respect to your full 1,000 examples. Just find the gradient with respect to 10 examples. Those examples form a batch. Okay, and you'll keep changing the batch so that you cover the whole data. And the second, I guess, more key point is why we're doing batch gradient descent. Why can't we just do gradient descent, which is in this box, and that's the right thing to do? Let's say the idea is that many times you'll have a lot of computational limitations which don't let you find the gradient with respect to your whole training data. Okay. For example, I think in your assignment 2, you'll be working with images. Okay, and let's say you have, you know, uh, in assignment 2, you'll have, let's say, 50,000 images. Okay, 50,000 images of whatever size. Each image, let's say, is an observation. Is a data point basically for which there's a class. It's a cat, dog, or fox. You have 50,000 images. Finding the gradient of the loss with respect to those 50,000 images is it turns out to be computationally difficult. Okay, for the computer to do, like for it to like really look at that graph and do this backprop operation. But you have to aggregate across those 50,000 observations because there's a sum, right? There's this type of sum going on. Is hard. Hard as in like it requires a beefy computer basically. And if you generally don't have beefy computer, you would resort to doing this batched approach. Okay? That's one reason why you do it. Maybe there are other reasons. The researchers are still trying to see, hey, batching, does it have other nice properties or not? But this is one of the reasons why you do batching. Okay. Um, any questions about this part?
Hi, Teja, it's CJ.
Hey.
So during the course of the semester with batch gradient descent and gradient descent,
Yeah.
are there any specific real world examples that you can point to that often
Yeah.
use this method?
Oh yeah, so what we'll see, I think from assignment 2 onwards, you will be using PyTorch, and you'll actually not be, I mean, we'll see today, for example, a small Python script where we'll explicitly be writing this, but there's these big packages like PyTorch by Facebook and TensorFlow by Google. They will have a function, they'll have basically a function like optimize, and you can just give arguments, hey, do this behind the scenes. You can just call that function. You can just call that in one of the statements in your for loop while training your model, and that will do it directly. And so we'll see a lot of real world examples, if, through assignments, as well as today we'll try to look at. In fact, right next, right after this slide, we'll talk about a code base, and so we'll look at it. But uh, in real world, you will not generally, for deep learning models, you would not write it explicitly like this, because you will generally be relying on one of these packages like TensorFlow, Keras, or PyTorch, and they will have a way for you to just specify, hey, optimize by doing gradient descent, or optimize by doing batch gradient descent. You just have to specify that, okay? And it's like a argument to your function call. So we'll see batching. So actually batching we'll see later. Let's look at gradient descent itself first, so that to get a feel for it. Um, yeah, I mean, I don't want to talk about. So there are different names for those function calls, but I don't want to get into that level of detail at this point. Once we get to see an example with, let's say, PyTorch or one of these packages, like some example code, then I'll just call out, hey, this step is actually doing just these updates that we have written here. Um, but it's a great question. At this point, it's unclear, but unclear like why knowing this is supremely important. But I guess the objective of the slide was, or at least the motivation for the slide was, 99% of all deep learning models are just trained exactly this way. I mean, with some minor variations on, hey, how do I find the gradient? Generally they will be using batch, and some minor variations on, they'll generally be iterative like this. Iterative just means there's going to be a for loop, and there's going to be some minor variation on this these equations. Okay, instead of w naught minus 0.1 times gradient, there may be slightly different update rule, but this pattern is the common thing, core for pretty much all neural network models. In fact, you can also train all the models that you've seen before, like support vector classifier, let's say binary classifier. You can also train logic regression, and we'll see code example right now. You can also train any of the models that you've seen. Generally, gradients are hard for models which are, models which are not, models which look like trees. Trees are somewhat discrete in nature. You go from a region to a region, basically. So for trees, you may generally not use gradients, although you might have seen gradient boosted decision trees. So there also you had gradients used. Um, so yeah, gradient descent. So this idea of using gradients to update your parameters to get to a good choice of parameters is the core underlying idea. Okay. Okay, so now I want to actually switch over to, so this last part of this lecture and the first part of next lecture, is just about looking at Python and getting a feel for a linear classifier in Python. So we'll do that now. So and we can revisit some of the questions that you may have. So let's see. Okay. Okay, so I think last time I had mentioned Google Colab. Um, so if you look at this, this is a syllabus page, and sorry, this is not a syllabus page. This is actually lecture details. If you go to the syllabus, sorry, this um, repository, and I can just paste this repository here in the chat if you want to try out Colab in real time. What you can do is, hey, this is the GitHub link. I can just go to open a new tab, and let's say go to Colab. Well, it's just a link. It's just collab.research.google.com. Collab, so that you don't have to do anything on your local machine to try out some of these things. Yeah, this is the link. So you'll see there is a bunch of tabs for you to do something. So what I did is, so one way to do something in real time is you can click GitHub. It will say some error, but that's okay. So you can just type so sorry, this is my name. Yeah. So you can just type this on the GitHub tab on Collab, the URL that I shared on chat. And if you press enter, you'll see a bunch of those notebooks. Okay, and in fact, assignment one, if you can directly click on assignment one and you can see the assignment one, but you'll also see, for example, you can open the syllabus page. You can also project page and so on, lecture details page and all that. What I want to show now is, so we can open is, and let me actually go back to GitHub. So you can see there's a bunch of files, right? Basically assignment files that are linked on the syllabus page, similarly the project description file and some lecture goals file. So there's also an examples folder. Okay. So that examples folder has a preliminary set of scripts. I'm gonna improve them as we move forward in the course. But one of the scripts that I want to look at is called linear classifier example. Okay, and in Collab, if you want to do it in real time, you can just pick examples slash linear classifier example. You can click on that. Okay, I can let's click on it. So to click on it, I'll get this Collab interface. This is the interface for, I think last time I did some very preliminary, like print something or and stuff like that. So this time we'll try to walk through this feed forward, sorry, this linear classifier example. This is actually a multi-class logic regression example, this notebook. And in between, I'll also try to motivate a little bit more about Python, because that's first part in the slides for the second module. So to get to this point, all I'm saying is use that link that I used in chat, use tejt/pl-notebooks as the part for the GitHub tab, and you'll be able to open linear classifier example. Okay, so I've already done that. I've actually opened another file. If you see in this examples folder, there's another file called Python review. So let me start with Python review first, and then talk about linear classifier. Okay. And what we want to get out of this, the next 10ish minutes or 15 minutes, is that hey, we'll get a little bit of sense of Python, but we'll also see that linear classifier is not good enough. Okay, and it's one of the I guess one small motivation for hey, let's look at something more non-linear, and that's where feed-forward neural networks can come in. Okay, sorry, neural network model class itself comes in, and therefore within that we'll look at feed-forward neural networks. So so this is a notebook that I just imported. Same thing. You can just do the same way I showed earlier. So this is a quick. Just what is this notebook doing? This is a quick notebook or a really short notebook to say how a few things are done, and how some of you have looked at R may feel a little bit comfortable using Python. Okay, so just like you would use RStudio to write things, generally you can use Colab. I would suggest for much of this course. It's recommended only because we also get to use GPUs eventually if you want. Like you can do hit runtime and you can do change runtime type, and here you can choose a GPU or a TPU, and you can get one of these things for free, as long as you have this one of this Google account or your UIC account, um, and that makes it way less complicated than trying to, if you have your own GPU, that's great, but otherwise this is one easy access to a GPU. So let me I know last time a lot of you mentioned that you're not familiar with Python, and I had recommended going through uh, going through the link in the syllabus page. There are a couple of links on Python right here. Right, so there's I think one of them is OCW, the other one is OCW or MIT, and the other one is from Stanford. So they gave a sense of how to write some preliminary code in Python. As you can see, Python you can, and by the way, we'll mostly be looking at Python version 3, and yeah, so version 3 is the standard, most of the standard these days. So 3 point, let's say 8. And so this is how, so this is a cell. Okay, so you can see on Jupyter Notebook, if you directly install Jupyter Notebook on a local machine, and there are ways to do that. I'm not discussing that in the class right now, but if you did that, you'll pretty much have the same type of interface, and you'll have cells, and you can in each cell, wherever my cursor is, I can do shift and enter, shift plus enter, sorry, to execute that cell. Okay, and so you can do cell, you can execute things in each cell, just like in RStudio or R. You would select a a statement, and then maybe press Control Enter or something to just run that statement, for example. Right, same idea. So here's so how you declare basic data types. Here are some examples: X, Y, and Z. Here, X is an integer. As you can see here, X is an integer, and Y is a float. Okay, so I declared X is equal to, so this is how you declare constants. And there are many ways to do these things, but here's how I have illustrated it. So X is equal to 3 makes X an integer. So you can type of that variable X to figure out what type it is. And this is generally sometimes useful, especially with later on in your assignments, if you want to know the types, as well as oftentimes you would also need to know, oh, if it's a matrix, how big is the matrix, and we'll see that in a minute. So this is how you do a division, for example, a multiplication, similar, and all that. Okay. So for example, if I do y/z, then I should get 1. Okay, so what it does is it does integer uh, uh, division. So 3 divided by 2 should be equal to 1.5. But if you do double slash, it only retains the integer. And in fact, because z was, sorry, if y was, uh, sorry, since y is float, it retains, it prints it as 1.0. But if I choose x divide double slash divide by z, then you'll see that it's 1. And the type, you can set it to another variable and print its type. Its type is going to be integer. Okay. This there are some ways that you can, so you can add comments by using this hash symbol. Uh, in R, I think it's percentage, or I don't remember now. Can somebody confirm what is the comment line for R? Is it percentage?
Professor is the same thing, I think.
Oh, it's hash. Okay, okay, and okay. I mean, so don't worry about it. And in Python 3, you have the print statement as a function. In Python 2, it used to be slightly different. Okay. And here is one example. So this y double star 2 is just saying, hey, set y is equal to y double star 2. And similarly, x plus equal to 1 is just saying, hey, x is equal to x plus 1. Okay. So if you run that, you get 4 and 9 respectively. Now, similarly, you can assign multiple variables at the same time. And and you can also have variables that are not numbers. And so, for example, the first set of variables a and b are booleans. Okay, they're not integers or floats, the usual numbers. And similarly, this my string is a string, and you can, if it's a string, it has its own, uh, although it's a basic data type, it has some nice functions. And generally, you would call functions. How would I know about this? You can look at uh, Python documentation for these types of extra, um, functions available for an object like a string object. Okay. So I'm using some words here like an object and so on. So let's I think folks who have seen object-oriented programming have ideas about what is a class, what's the object, and everything else. But folks who have not seen it, that's fine. Just generally think of an object as like a container which has a bunch of functions and maybe some data in it. Okay, so data and functions are together. Just think of that thing together as an object. So what I wanted to show you is like a couple of data types that you will kind of use repeatedly in much of your code, especially some pre-processing stage. Trying to get your data into a situation where it's going to be, hey, feature vector, here's a label, and then pass it to your model, right? So when you do that, like for example, for pre-processing or even for model training, you would generally be dealing with some data um, structures. So these are a list, a tuple, and sometimes even a set. So a list, a tuple, a dictionary, and a set. Those are the four data structures. So a list is, as the name implies, this is a collection of things, okay, collection of elements. It could be a collection of these strings, okay, one character strings. It could be a collection of integers. It could be a collection of strings and integers, and it could be a mixture, okay, of both, and so on. Similarly, a tuple, the slight difference between a tuple and a list is that a tuple is it cannot be changed. So in my list, I can change the first element as I show in the next cell, but in my tuple, I cannot do that. Okay. So here's just printing out the tuple and the list. So what I said earlier is that in my list, I can change the first element. So Python indexing is from 0. So you can change elements in the list by setting them, by calling out. Okay, I didn't define it. By setting the first three coordinates to be C, B, and A. That's what we did. And you can also, there are a few extra nice things, like you can append an element to a list and a single element, like a number or a one character string. You can also extend a list with another list. Okay, so this 7, 6 with square parenthesis is also a list, and so you can extend the list. Okay, so beyond the basic data types that we had integers and floats, and of course some extra things like booleans and strings, uh, pretty much some working knowledge of a dictionary, a list, a tuple, and a set is also not that critical. A dictionary, a list, and maybe a tuple will understanding them well. Trying out small examples will help those who have who have not seen Python. Understanding these three data structures would really help. Okay. Um, yeah. So next is I want to spend a few more minutes on lists and then some functions and so on. So given a list, you can index. Okay, and this is something you will see in the logic regression code later. You can index elements of the list using this notation. It's very similar to what you would also do in R or MATLAB or other things that you might have seen. So for example, this is saying give me a list of, so give me a subset or a part of this list up to the second element. Okay, not including the second element, up to and not including the second element. So the zeroth element, so here actually we are setting the first two elements. So I'm just saying set the zeroth element, set the first element, because I'm saying up to the second element, not including it. So there are two locations where I want to change. So I'm saying, hey, we can change those two locations using these two values. And so if I print this, first locations have been changed from CB to A comma A. Okay. Set is a different data structure which basically does not let you keep repeated elements. Okay, so for example, you see here in this list there are some repeated elements, namely A is repeated thrice, right? So if you call set on this list as an input, you will get an object which a set basically which will not have A repeated 3 times. Okay. Um, and finally, let's talk about dictionaries. So a dictionary is a really nice. It's a very good abstract data type that you'll see in many different languages. But it's basically a lookup table. Okay, so there's basically a notion of keys and values, or a lookup table where you can say. So if you look at here, I'm creating a lookup table called or a dictionary called course, whose uh, key is going to be my tuple, and its value is going to be advanced prediction models. So think of it, it's like an Excel, a 2-column table where on the first column there's keys and the second column there's values, and you're able to non-linearly like instead of like indexing trying to find the row of the of your 2-column table by using, let's say, an index. Let's say give me the 5th row. You can say, hey, give me the value corresponding to this key. Okay, and you can do that. For example, here, my tuple is the key and the value is advanced prediction models. If I say if the key is, let's say, let's say the string 572, maybe the value is data mining. So um, you can see that this is the key and this is the value. And let me so courses, sorry, course 576. So if I ask for this, oh, it's not 576, but 572. So I got the value, which is data mine. So that's the very simple idea. And once you understand the simple idea, you can actually use it. Maybe not in a performant way, but as a beginner, this is a very useful object to work with. Okay. Now here's a very simple example of a for loop. So that previous gradient descent code would be like, hey, give me W new is equal to W old minus, let's say, 0.1 times, get me the, tell me the gradient with respect to gradient of the loss with respect to W. So where I am able to somehow compute this using, let's say, backpropagation. in a previous step. So you would do something like that. Okay. Um, yeah. So this is a for loop, and this for loop is probably similar to R, but maybe without the parentheses and closing brackets and all that. The second thing which I kind of forgot to mention earlier is that um, Python is sensitive to indentation. Indentation is like how far away is the next statement. For example, within the for loop, there are a bunch of commands going on. In particular, there's just a single command, print here. So it's indented with 4 spaces. It doesn't have to be 4 spaces. It can be 2 spaces, or it can also be a single tab, or it can be something else. But you just need to be consistent with that indentation, because that's important, especially because we don't have braces and parentheses and all that. Okay, so that's a for loop. Uh, and here's a function, and we'll see a function pretty soon, which is, or maybe we'll not have a function. But this is a function which implements the function that we saw earlier in the BackProp example. It's 1 by 1 plus e to the power minus z. Okay, so for that I need to import a module, a Python module called math. Okay, you can call it a module, a Python package, and I'm also calling another very important Python package called NumPy. And so using NumPy and optionally math, you can actually, you're able to write all sorts of those all sorts of functions. Okay, and especially with NumPy, you can represent vectors, matrices. I think in the last lecture I was saying that we can represent an image using 3 matrices, one below the other, right? So that was actually a 3D array, and you can also represent that. So so here's the function again is written this way. It's like def space function name bracket input arguments. Actually, you can make it better if you specify types and all that, but this is a simple example here. And then the function returns some value, in this case, the softmax expression, okay? The 1 by 1 plus e to the power minus z expression. And then I'm calling softmax at different values. Um, then you get some output. Now, just as a teaser, if you use something like PyTorch, uh, that package can not just do this forward pass. So given input, it produces an output, but also does your backprop computation for you, so that it can tell you what the gradient of output with respect to input is, okay, automatically. Um, so so that's something that we'll maybe see next lecture. So next, I don't want to spend too much time on NumPy, because we've already covered quite a few things for you to go back and check if you have not done, since last week, to try out functions, try out dictionaries, lists, tuples, sets, and generally play with printing statements and for loops. Okay. The second thing, once you're a little bit more comfortable with these basic data types, then you should start looking at NumPy. Or you can also directly pick up PyTorch and play with PyTorch based uh, matrix and the array representations. But NumPy is a standard very popular package. It is complemented with SciPy. Those are the two packages that are generally used for scientific computation and math related computation in Python. So NumPy, you can define an array. So if you define an array like this is a um, vector, okay? So A would become that vector, -1, 0, 1. But if you want to specify a list of arrays, then it becomes a um, um, 2D array, basically. So its type is going to be ND array. And with that, you can actually also call, hey, what's the shape of this array? And tell you, hey, it has 2 rows and 3 columns. Okay. So this 1.0, 2, 3, let's make it 4, 2, 3. You can see that this array has 2 rows. It's basically exactly the same as what's written here, this row and this row. And the shape is 2, 3. Okay. And the first one is also an ND array, but shape is the second output is missing, because it only has one uh, row, basically. Okay. Um, let's see. So there's, I don't want to spend too much time on these at this point. Maybe we'll revisit these. I want to use specific examples in the linear model that I want to talk about next. And so I'll skip some of these, but maybe we can come back to this towards the end, or maybe in the next lecture. Okay. And also you can see images, you can read images and so on. So this actually does not work on Colab because it's not a local directory, but we'll talk about how to read files, or read things, for example, from your computer and all that, when we talk about that linear model example. So any questions about just Python in general? My objective is to get you familiar with it and not be scared with respect to Python, especially if you've done assignments in R from one of your previous lectures or previous courses, or even something parallel to this, then you should be fine. Okay. And while there is a whole process of setting up Python on your own computer, uh, this is one easy way to, like, I don't want to deal with all the logistics. Let me just try out the language, with the syntax and with the basic data types. And Colab is a great way to get started with that. Okay, if there are no questions, I see that I have already exceeded some time. So actually, I wanted to give you a 10-minute break. So let's resume at 7:48 and continue from there. Yeah, and yeah, we'll do that. Yeah, so instead of, so what I did right before the break was I was talking about NumPy, and I think while NumPy has really nice support for n-dimensional arrays, the key thing that you would like to learn, you should learn, I think you will use NumPy maybe in your assignment 1, is indexing. Okay, indexing. Let's say you want to get the first column of a matrix, and how do you get it? How, if you want to get the third row of matrix, how do you get it? Or if you have maybe a tensor, which is a three-dimensional matrix, then how do you get it? There is some information regarding that on that notebook, but I wanted to um, this notebook, uh, but I wanted to not spend too much time on that because I want to show you a linear classifier, which is exactly the W and B that we saw in our lectures last week and this week. It's basically, we're going to use W and B as parameters of this model. And so let's really look at the model, and let's look at a very, I guess, in a lot of detail, the backprop step. It's just for as an educational purpose to see, hey, this is how a model is trained using the gradient descent approach. Okay, so um, so so here's a Python script, and this is a linear classifier example from that examples folder. You can open it if you want in real time in Colab. The only thing that will be changed is that instead of reading from disk, which was what the notebook in the original notebook was doing on GitHub, I have just copied the way the data is generated here. Okay. So what's happening in the first cell? First cell is just saying, hey, import key things, NumPy, and plotting object, plotting object, and then if you want to keep experiments repeatable, generally what you do is you set the seed of a pseudo random generator that will be used to generally a random generator is used underneath or behind the scenes by the Python kernel to generate random numbers. Okay, so if you set the seed, you get the same random numbers the second time you open the book and run this whole code. Okay, um, so we just ran this. So sometimes you will have packages which are missing. So what you would do is, at least on Collab, or even you can try this on other places as well. You will say pip install NumPy, for example. NumPy is already there, so it will not do anything. But if it's not there, you can install it. Okay, sorry, you can install it. So here we're not doing anything. So this is where you can see an example of dictionary. So don't worry about what's happening here. It's just some parameters to this plotting plot object has a field. As I said, plot, think of that as an object, which is a field, which happens to be a dictionary. Okay, so the dictionary is called RC param. So you can give key and a key and a value to this dictionary. This is params dictionary. Params just means, I guess, parameters. So you can see that image interpolation. Hey, this for this key, you need to say, hey, nearest is the value. Okay? So you can set parameters, for example, using this. So now let's look at data. So here we're using some aspects of NumPy that I wanted to highlight. One is we're picking three numbers, right? Three integers here. And then I'm saying x is equal to NumPy. So by the way, NumPy is imported as NP. So if I did not do as NP, so this is a short form. If you had a complicated, very long name, you can do import something as something. Okay, or so you can do the shortening, and we've done it here. So you can say x is equal to numpy n times k comma d. Okay. So what does this do? So let's look at. So by the way, the whole benefit of doing this in such a notebook, there's some pros and cons, but one of the benefits, especially for somebody who, where we're doing a one-off like experimentation with a training a model under training and pre-processing the data, this is very useful. So you can open another cell and see, hey, what will happen if I do np dot zeros, let's say 4. If I give 4 as an argument, I get an array, an numpy array with 4 zeros. So what will happen if I give 4 comma 4? Okay. So you can see I get a matrix with that size. So what I'm trying to do here is I'm trying to get a matrix which has the number of columns to be D. Okay, so D is the dimensionality of my data, is dimensionality of my features. I want to keep it 2 dimensions. And how many observations, so how many rows do I want? Remember, if rows, think of them as the number of observations. So what I'll do is I'm trying to generate a 3-class data set. Okay, and so I'll have 3 times the number of observations I want to have in each class. So that's what's going on here. So focus more on np.0. So that's a very convenient way to create a matrix with all zeros. Okay, and and I'm also creating an np.zeros now with a single argument, which is n times k, which is 300. And I'm also explicitly specifying the data type, that it should be an integer. Okay, it doesn't, I can do a casting to an integer later, but here if I say data type is integer as an argument to this function, then it creates the zeros vector. Okay, so you can see this in action. Actually, here I can do the type is equal to u int 8. So if I do this, then each element there'll be you'll see the dot vanished. Okay. Um, yeah. So here, I mean, so we'll not parse this particular for loop. So this is an example of a for loop, and just like in the previous review code, there was a for loop which just printed something. Here, you should go back and see, hey, what is each line doing? For example, for example, here there's a function called range. I'm using that to say I want to use this for loop variable j going all the way from 0 to k minus 1. That's what doing in range k will do. Will do. So you will learn that when you look at the intro Python notes that are on the syllabus page. Uh, so again, range is being used, and then this is a specific NumPy function. So actually on Colab I think you can see the function definition just by hovering on it. Oh yeah, but that's a huge yeah. So it says here, return evenly spaced numbers over a specified interval. So in that sense, so hopefully that will help you in understanding what is each, function call doing, linspace or even zeros. Um, oh, it's a built-in function, not much definition. Linspace, there's some definition there. See, both are built-in functions. Okay, but so we'll not pass this for loop for now because I want to get to a few other parts of this code base. So if I run this, we'll get the data. Okay, and I want to look at some important sequence of steps are happening in the for loop. So where we are doing something for each class. Actually, we are generating per class some bunch of points. But once we generate them, here are some extra. So in this cell, we're gonna look at the data. Okay, since it's two-dimensional data, we can actually look it on a plane, and therefore as a graph very easily. So you can see here, since it was a matrix, I'm calling dot shape. Okay, so dot shape gives me both the number of rows and the number of columns. I only want to know the number of columns, so that's why I said, dot shapes. It's a tuple. It has 0th index being the number of rows and the first index being number of columns. So I want to pick the first index, so that's why I'm saying square bracket 1. Okay. So so for example, yeah, let me run this first, and then so this is the data. So you can't see the third class maybe not that clearly, but there is a red class, there's a blue class, and there is a yellow class. Okay, so if let's look at D. So D is just 2. But if I did x, x dot shape, then I would get the two numbers. Okay, a tuple which is 300 cross 2, and I'm picking the second one. If I pick the first one, I would get number 300. Okay. Uh, so this is the data set, and we're going to fit a logic regression classifier to this data set. So at this point, so we have also used the scatter function here to draw a scatter plot. To see how different plots can be generated, actually Colab itself has a nice, so if I open Colab again, although I won't be able to probably open too many such notebooks. So you'll see examples. On the examples tab, you can see there are a bunch of examples. So in that, if you click charts, you'll be able to see a bunch of how to plot scatter plots, how to plot. So all the things that you might have done in R or even Tableau, not all the things, but some of the things, you'll be able to kind of see how to do that. Okay, but let me come back here. Any questions at this point about Python, or mostly Python?
Professor, could you please explain what is x of ix? I did not understand that part.
Okay. So what we are doing is, so I skipped over this. So just think of ix as a bunch of numbers, indices. So let me actually, so you can actually print ix. Ix still probably here. So it's a range between 200 and 300 for the third class. Okay. So this is a for loop over 3 classes. Okay. Saying for j is equal to 1, do something. For j is equal to 2, do something. Actually, for j is equal to 0, also do something. Okay. 0, 1, and 2. Okay. Now, this ix for the last one, the last option when j is equal to 2 is range 200, 300. Okay. Now, what it's doing is just selecting those rows of your matrix. Okay. It's just selecting those rows. So I think I skipped that, by the way, when I'm talking about NumPy indexing. There are many ways to index rows and columns. I would suggest look at this offline. Uh, uh, but yeah, it's basically picking those rows and saying, hey, on those rows, the feature value should be something, and the class should of course be the third class. Yeah, third class. Yeah.
Okay. And
Yeah.
c underscore is a function of NumPy.
Yes. Yes.
And what is the line space?
So linspace is a way to generate values. So sorry about that text. I don't know what that is, but if you look at this, it returns evenly spaced numbers over a specified interval. Okay. So for example, here's an example. You can just see, I think, yeah, here. Linspace 2, 3, and if you want 5 numbers, then it'll provide, since you gave the starting interval value, ending interval value, and numbers, it'll give 2, 2.3, sorry, 2.25, 2.5, 2.75, and 3. You may have a similar function R, but I don't recollect the name.
Okay.
Step maybe. No, not step. Sorry, step is that argument in that function, but I don't remember. If somebody remembers, maybe they can tell us. But yeah, it's just like trying to create a bunch of like evenly spaced points. Okay?
Got it.
So how many such points? Capital N number of them, which is 100 such points, okay? Between 0 to 1. Yeah.
Okay. Thank you, Professor.
Any other questions about? So don't worry about this. This is a code to just synthetically generate this particular data sets. Okay, so it's saying for like one of the classes, tell me, get me these blue points in this 2D space. For one of the classes, get me these red points. But more than that, I would suggest focus on, hey, this is how I would use some of the functions in NumPy. This is how I would write a for loop. But the actual code, like what is in, sine and cos and all that, we don't care. It's some way of saying, hey, these are the features for which I need to assign labels.
When will we have our first lab session?
So lab sessions are actually optional. So it just depends on the demand of the class. The TA will, so it's not pre-scheduled, right? So it's not every week. I mean, it can be made every week depending on how much support you guys want, I would say. So right now the TA, I've told the TA to be on standby and be ready for a few sessions, but it depends on if you want help with this or do you want to help with something else, because we have about 12 plus weeks to work on this.
Okay.
Yeah.
If at
But
all,
I think instead of lab session, I do highly encourage you, since the class is small, do reach out to me or the TA. We will have one-to-one discussion on something specific, because the lab session is like broadcast medium again, right?
Yeah.
Um,
I think that will be really helpful. Thank you,
yeah,
Professor.
so actually in assignment 1, you will have to know a little bit about this code to be able to do some modifications
Uh,
for one of the questions. Um, Um, but yeah, but just to not lose sight of the overall context, the objective here was to just show the gradient descent step, okay, and also the model specification, how we're able to optimize or minimize the loss function. Okay? And if we use linear models, and that's where the w comma b that I was using as parameters from last time is basically for this linear model. It's not enough. I mean, you can see if I create a linear decision boundary, linear models generally produce linear decision boundaries, and decision boundaries are just the basically lines on this 2D plane where you cannot say whether this is of class A or class B, basically. Okay, so there's like some boundary lines where on one side it's one class, on the other side it's other class, and you can already see that this data set is curving so much that you probably can't get clear class boundaries which have zero error, for example, training error.
and
But
also, Professor,
yeah,
one more question, one more request is, could you please upload your schedule so that we can like ask you for a session, like if at all you have any slots in betweens.
I, I think you just I can make time, right? I
Okay.
mean, since it's offline, sorry, since we are online, we can just negotiate. And if let's keep it simple. Whoever wants to reach out, let's initially reach out to me, and then let's we'll probably schedule something the next day or at most 2 days later, and see how much that is complicated. If that process is, I think that that's a simple enough strategy. If that is not working out, then I'll send out a schedule and more, keep it more structured. But I right now I don't know many of your schedules, so for me to suggest a schedule and then nobody is able to make that time, and it will not.
Okay.
Let's try a very simple thing. Just email me. Let's have a 1:1, or maybe a group can reach out to me, and me or even Teng Teng, who's a TA. We both can help you out.
Okay. Thank you, Professor.
Especially Teng Teng. I mean, she has dedicated hours for this. Especially helping with Python, she can definitely do pretty easily, for example.
Thank you.
Um, So let's go to the model part. So for us, we don't care about how the data was generated. At the end of the day, we need we need the data as the input, right? So actually, the modeling part comes at this cell where somebody, if the data is on disk, you just have to read it and make it into an x matrix and a y column vector, right? So where each row of the x matrix is an observation, and in each coordinate of the y vector will be the label. Okay, as long as you have those x and y objects, okay, you're done, right? So the data is there. Now let's focus on model. Okay. So for model, um, this model will have, so it's a linear model. So there is some, again, you can see np dot zeros being used here. And then W has np dot random dot random. Okay. So what does this do? Let's actually figure out. So what is D, I don't know. So D we saw is 2 and K is 3. Okay, so this model has a matrix as one of the parameters, which has 2 rows and 3 columns. Okay, so this is a little bit different from what we saw in the lecture notes, where if we had 3 classes, then the number of rows had to be 3. Like remember, I think last time I showed um, uh, like if you had, so typically what you would say is, uh, course, so I don't want to use, yeah, course is, let's say this is, I don't want to say equal to. So let's say this is a 3-dimensional vector, and let me actually make this cell text cell. So scores is 3-dimensional vector. First point. Second thing is, in the notes we saw earlier that we would say, hey, whatever be the input, W times X plus B. Okay, so let's say input X is 2-dimensional. So in the notes from last lecture, then my scores is equal to Wx plus B. And here, W should be, you can see that scores, since it's 3-dimensional, W should be 3 times 2. And B should be 3 times 1, right? So this is what the notation we in fact used in the lecture, where 3 classes were cat, dog, and fox. If you don't remember, just go back and you have the recording, have a look at that portion offline. So this was what I said, and scores are just in logic regression. What happens is these scores, if you recall the part about the objective function, these scores get squished, okay, to be between 0 and 1, and this is exactly the softmax operation. So e to the power score divided by e to the power all scores, right? The 3 scores. So we have seen the softmax operation last lecture. That's just a recap. So once you squish this, then you feed this into a loss function. So this is what we discussed last time in the lecture. But you see here, W is the transpose of it. Okay, and why is it transposed? Why it's transpose of it is because W is not 3 cross 2 here. W is 2 cross 3. We saw that D is 2 and K is 3. K is the number of classes, so it's 2 cross 3. So it's a little bit different, and the difference is only because there's a transpose operation. Just think of it this way. So whereas score is equal to W cross 3, I can just write scores transposed is equal to X times W transposed plus B transposed, right? That's exactly is going on. X transposed times W transposed. Okay, so this is what's going. We're going to use this notation because why are we using this notation? You'll see that this lets us do vectorized computations. Remember, loss we had to compute per example. Now examples are arranged as rows, so it's easy for me to, if array examples are arranged as rows, X transpose would be a row vector. And so if these are rows, then I can just multiply with W matrix, W transpose matrix, and then I can get all the like scores and so on. So it makes it a little bit easier. So for now, don't worry about this. So this is what we saw last time in the lecture. Here, I'm going to specify W to be a transpose version of it. But there should not be any confusion in terms of, hey, why are you working with transpose and not the original one? It's just for some convenience in terms of like working with the data. Okay. So let's do the following. So let me run the cell. So I ran the cell. What we have done is just initialize the 2 variables. Okay, so if you look at B, if you just B and then print, then you can see B has been initialized to a vector which is 0, 0, Z. In fact, it's been initialized to a matrix. Okay, this B has been initialized to a matrix. And why is that? Because I can do B dot shape to see it's a 1, 3 matrix. If it was a vector, it would have shown comma nothing, right? We saw that I think in the review part, right? So it's fine. So it's B is a matrix. Similarly, W is a matrix. Now in the rest of the notebook, all we're trying to do is find the best B and the best W. Okay, and we're going to do that by minimizing a loss function. And how are we going to minimize loss function? We're going to use the gradient descent idea. Okay, so is up to this point clear? Any questions? Is it too slow? I mean, I know some of you maybe experienced.
Professor,
Yeah.
I don't have a question, but I think you want to put an R in the scores transposed, because right now it's scores transposed.
Yeah. So sorry, this is, by the way, this cell is not, yeah, good point. Sorry. Oh, it's even worse. Yeah. So by the way, this cell is a text cell. So I changed it to, I hope I did change it. Yeah. Like if I execute it, it's just going to be bullet points. Oh, it's not. How do I change it? Text cell. No, edit.
Can you hover over that area and then you get the text and you just can copy and paste it in the text. Over near yeah, like the line over yeah, just after that. Could you please hover? Oh no.
Okay, let's not worry
Yeah,
about this.
we just got it.
Um,
You got it a while.
oh, I got it. Okay, it's fine. I think it's not a big deal. I think I should have just inserted a text cell. I now have. I thought there was an easy way to just change the cell type to. Okay, maybe it's only keyboard based, is it? This change. I think I should look at the command palette, maybe keyboard shortcuts. Okay, add, convert. Yes, convert to a text cell. Control plus right? Control M plus M. No, Control M. Okay, let's try that. Command M. Oh, no, that minimize it. Okay, I'm not going to do all that. Let's not worry about it. Okay. So yeah, now what I said is we're going to optimize the W and B parameters. Okay, W and B, and what is fixed is the data. Okay, so for that, we're just reading that what is the number of examples. We already know it, but if you do shape comma 0, it will give the number of rows of X, the matrix, and we know it's 300 here. And here is the alpha. Remember, there was an alpha in the gradient descent update. There was a previous weight minus some alpha times the gradient of the loss with respect to the parameter. So the alpha, I'm just choosing it to be wow, it's choosing to be 1. But okay, it's 1 here, but we can change it if that doesn't work. Okay. So this is just scientific notation, 1 e minus 1, or you can just write 0.1 if you want, or just 1 if you want. So here's the gradient descent loop. We're doing 200 iterations of this W0 B0 to W1 B1 to W2 B2 to W3 B3, where the sub index, when I say 1, 2, 3, is just the index of this for loop. Okay. So here's the first evaluation. I'm going to do a multiplication of the X matrix with the W matrix. And that's where this transposed W was useful, because X I already know it has 300 rows and 2 columns. And if I multiply with this transpose W, which has exactly 2 rows and 3 columns, then I should get 300 rows and 3 columns. Okay, so in fact, I can execute this since X and W are already defined here. So if I execute this, let's call it some temp variable. And what I want to do is do temp dot shape. In these types of Jupyter environments, you can actually just you don't have to type print. You will actually see the shape. The last thing is generally gets printed. So you can see the shape of this is 300 cross 3. So why is this 300 cross 3? Remember, we had 300 observations, and for each observation, we want the 3 scores. Whether it's in here, it's not dog, fox, cat. Here, it's one of the colors. 0, 1, and 2 are the 3 classes. But for each observation, these are the 3 scores. These are not exactly the 3 scores. Actually, you also need to add the plus b vector, the 3-dimensional vector, to each of these to this computation, because each observation, the scores were supposed to be the W matrix times that observation plus B, right? This step here. And that's exactly what we're doing for each observation in a vectorized format. Okay. This step. Next, we are squishing those numbers. Whatever the scores are, we are squishing them into probabilities. Okay, that's what's happening. So this is the vectorized operation. Again, you can check up what np.exp does. It's exactly shown here. In fact, um, I lost the. So you can see exp does exponential of all elements in the input array. So it just computes e to the power scores for every element of the score. So there's so many score values because we're looking at all the observations together. So we are not doing any batching here because our most total data set only has 300 observations. So exp does exponentiation, and then you can do, and you can see this is also a vectorized operation. You can do a for loop here to deal with each observation, but here we actually do vectorize. So exp scores is actually again a matrix which is 300 cross 3, and we are dividing it by e to the power the first coordinate plus e to the power score of the second coordinate plus e to the power score of the third coordinate. Okay, so I will not tease this out right now. Okay, this is actually part of your assignment as well. But at least I want to get to the structure of this for loop before we run out of time. So the next step is this L that we saw in the class. Capital L is L data plus regularization. Okay, and regularization you can see is 0.5 or lambda times what is reg? Oh yeah, reg is 1 e to the power minus 3. I don't know why we wrote 0.5 there. Okay. Yeah, okay, this is fine. So this is some constant, 0.5 times 1 e to the power minus 3. You can see the reg is 1 e to the power minus 3. So sorry, by the way, 1 e to the power minus 3 is just like I can type reg here and see what reg is. It's just 0.001. It's not e to the power minus. It's like 1 into 10 to the power minus 3. Okay. Anyway, come back to this. So we have the data loss being computed and the regularization loss being computed, and both of them are getting added to tell me what the loss is. Okay. So for a given W comma B pair, we are computing scores, we are squishing them to be probabilities, and then we're computing the loss up to this point. Okay. So this is a print statement. If conditions are also very useful, especially for beginners. It's a little bit different from what you saw in Python, but it's basically saying, hey, if the for loop, this gradient descent for loop, if I is, if I divided by 10, has a reminder. So this is a reminder. So you want to get, you get the quotient and the reminder whenever you do a division. So here saying, hey, is the reminder equal to 0? If it is 0, then say, hey, which iteration it is. Instead of printing loss every iteration, you're just printing it a few times. Okay. This is just for logging purposes. Now, here's the part which, these 3 steps here, are about computing the gradient. Okay. So gradient is represented using, here we are not writing that inverted triangle L subscript W. We are just saying, hey, the gradient is dW. Okay. And for B, the gradient is dB. Okay. I will, in the interest of time, again, I'll not parse exactly how this is computed. In fact, this is part of your assignment. So maybe we'll have conversations one-to-one if you're facing difficulties with this part. But basically, we're getting gradients of the loss here with respect to inputs. For us, the inputs are parameters. I want to say, hey, what is how does the loss change as I change the parameters? Okay, the 2 parameters are W and B, so I can tell the gradient with respect to W, tell the gradient with respect to B. And in fact, how are these computed? These are exactly computed using BackProp idea. Okay, so first we find the gradient of loss with respect to scores, and then we know what's the gradient of scores with respect to parameters, and then we mush them, like put them together, okay, using chain rule. That's what's happening here. It may not seem apparent that way. And once we get the gradient, there's also another part of the gradient. Actually, this gradient also needs a gradient number from the regularization term. So this was just a gradient from the loss term, right? Data loss term for the W parameter. And there's also a gradient with respect to the regularization term, because regularization, if you see, it's only on the W parameter. And there are some reasons for that. I think last time I was saying, if you also regularize B, which you can certainly do, you are saying that the intercept has to pass through 0 essentially in some sense. Okay, if you've done linear models, you would generally not. If you did ridge regression, for example, you generally not regularize the intercept. You're not claiming that hey, intercept should be as close to 0 as possible. That's not just generally not a good idea to do that. Okay. So anyway, so dw together. So this plus equal to is just nothing but equal to the w plus regularization times. So plus the gradient of regularization with respect to w. It happens to be equal to w itself. Okay. Anyway, so these two variables happen to be of the same size and shape. So it's the same shape as the parameters. Okay, and that's a fact for gradients. Okay, if you're taking gradient of some scalar output with respect to parameter, the parameter happens to be a matrix. Okay, then the gradient with respect to the loss, a scalar value with respect to the matrix is actually same shape. It's going to be a matrix. Okay, so dw is a matrix. You can see this again, instead of plus equal to, let me write w, which is the previous value, and this is p, the previous value. So previous value minus step size, which we just saw, it is like 1 or 0.1 times the gradient. Okay, so this should work because this is a size 2,3. This is also size 2,3. So this new updated w is 2,3. Okay, so let's try running this. I hope I didn't change too many things. Okay, I mean, there is some print out every 10 iterations of this for loop, and you can see the last value at least decreasing. Okay, so it's not decreasing too much. Certainly, it can. Let's try increasing. Oh, we already step size 1. Okay, so maybe let's see what the performance of this model is, in the sense that when we did this 100 iterations, we finalized. So at the end of these 100 iterations, there was some final W and B value. Okay, so those are, we would say, our candidate best model parameters. Okay, and what we need to do next is to see, hey, how does it work on a validation data set? And that's what we want to do. Unfortunately, in this script, we're going to do a shortcut. Our validation data is going to be the same as our training data. It's a bad idea, by the way. We're going to just do, we're just going to look at in-sample fit here. But in real world, you should not do this. You should have a separate validation data set. I think you might have done this in 572, so I didn't want to emphasize too much on that direction. Okay? So I'm just taking X test to be the same as my training data, Y test or Y validation to be the same as my training data labels. Okay, and so what I'm trying to do first is, hey, for this test data, first get me the scores, and then tell me what the predicted class is. It has to be one of the 3 classes. And again, I'm using a nice function from NumPy. It's called argmax. And I think we saw that argmax earlier in last lecture, which is like, if you have 3 scores, let's say 3 scores, tell me the index of the score which is the largest. Okay, and so generally your model will have a high score for that coordinate which it thinks is the right class, right? So for example, scores, if it's 10, 5, and 3, then argmax of, actually, in fact, let me do this here. np.argmax of, I don't know if it has to be list. Let's try this. Yeah. So you can see argmax of this. So it generally has to be an array, but even a list works. So you can see argmax of this, let's say this 10. So argmax is the last coordinate. But what if I change the first coordinate to be 100? Now argmax should be the index of the number, index of that element which has the highest value. Okay, so index of this number 100 is equal to 0. So if I execute that cell, so you can execute by clicking on that or press shift and enter, you can see the index is 0. So that's what argmax is. So, and if I get the argmax, that's my predicted class. So right now my classes are encoded as 0, 1, and 2. There are 3 classes. First class is 0, second class is 1, and third class is 2. Okay, 0 indexing. So this is how I'm getting my predicted classes for each of my test data points. Okay, and then I'm checking, hey, is the predicted class the same as is predicted class the same as what's there in the test? Okay, now this is actually a I would say this comparison actually is vectorized. Again, you should print this out and see, hey, y test is not a single number. It's one, it's one label per 300 classes, and similarly predicted class is also one label per 300 classes. And so this equality is saying what is the number of locations where the true class, sorry, the class true class matches the predicted class. Okay, and you're just looking at what is the mean value. It's just a shortcut, again, a numpy function to say what's the mean value of these this equation, this intermediate vector here. Okay. So let me execute that actually. So it's saying uh, uh, the mean number of times, like the performance is 50%. Okay. Remember, this is a 3-class classification problem. So 50% a priori doesn't mean that it's bad. Okay. If you were doing 50% for, let's say, balanced 2-class classification problem, then you're bad. Right? You're only saying half the time you're right, half the time you're wrong. Okay. But 50% plus for 3-class, especially when it's balanced, it is balanced in our case, seems pretty decent. But let's look at the plot. Okay, so let's not go into the details of every line here. As I said earlier, in Colab, there is a sheet which talks about charts, and that's a good way to get a sense of different types of plotting and different plotting packages themselves. So let's execute the plotting thing, and you can see this is the 3 classes. Okay, so what we're doing actually in this above cell is saying, hey, pick every point in this 2D space and classify it as blue, red, or green, and whatever the color is, that's the color I'm going to display. Okay, so you can see that this is the 3 classes. You can see red, this region, this decision region is where we are saying any point here should be red, and any point here should be blue, and any point here should be yellow. As you can see, it does capture a bunch of points in the same class, but it also captures other things, and that's the limitation of linear classification. And you've already circumvented this in your previous courses when you did, let's say, SVM with kernel trick and so on. Uh, like, although it's not for 3 classes, I mean, but you can certainly do SVM with 3 classes with a little bit more extra work. So you've already seen nonlinear models like random forests or gradient boosted decision trees. They're all nonlinear models. They can certainly capture this pattern. Okay, they don't have to have linear decision boundaries. In the next class, we will look at feed-forward neural networks, and we'll see that it certainly captures this pattern. Okay, that's not evidence that neural networks work. Okay, that's just an example that this is a illustration to show that linear models have their own limits. Of course, and deep neural networks are one ways to get around those limitations of being able to capture much richer decision regions. Okay, but of course, deep learning does a lot more than just being able to be nonlinear. And so that's focus of this entire course. So we'll slowly unravel those ideas in the course. Any questions in the last couple of minutes?
Yes, I have. Yeah.
Mhm.
Why we initialize b equal to 0?
Those are some great design questions. So we don't have to. We can also do random numbers. In fact, W also we can choose random numbers. Okay, you can. So it's a good exercise for you to also think about why. So how does initialization matter? Initialization actually doesn't matter for this model. This is a linear model, and it turns out that the loss function is like a ball. Okay, so it doesn't matter what the initial number is. You will always go to the bottom of the ball where W and B are the best choices. Okay, and the best choices are exactly this, right? So can you imagine a better like cutting of this three regions than this? Probably not. Okay. So, but initialization has a lot of impact in deep neural networks because they are nonlinear. Okay? And initialization, whether they're zeros or non-zeros, it really depends on if you initialize all of them to zeros, it should not happen that your gradient is 0. Okay? If your gradient is 0, okay, if it's a nonlinear model and your initialization is 0 and your gradient is 0, then your new number is also 0, a new parameter number. So it's just, as long as you can avoid that, any initialization should be fine. But you'll see in neural networks, there are some heuristics around certain initializations and so on. And we'll see that in the next and subsequent lecture.
And what about the 0.01?
Yeah, those are all design choices. A great question. Thank you for asking. So, for example, this, sorry, not this. Yeah, this, for example, this regularization parameter, you need to pick that. There's also, where is the other thing? Sorry. There's also step size. We need to choose that. These are all choices that we need to make. Okay? So you can say, hey, I'm going to do this choice, finding out the best choices using cross-validation. You can do that for this type of data set. In deep learning, that's a challenge. Like, because each run here, it ran in like within like 10 10 seconds or something. But with large data sets, image data sets, it's not easy to find these parameters very easily. And there's this whole subfield of hyperparameter optimization. So these are generally called hyperparameters because they're in addition to the core parameters W and B. So optimizing them is there are a bunch of techniques there. Although since we don't even know how to, what the model specification is for many of the neural networks, we'll talk about hyperparameter optimization maybe later on in the course. But yeah, choosing step size, choosing regularization value, or for example, and also choosing, for example, why 200 rounds, right? Why not 100 or why not 1,000 here is also a question. Yeah. Great questions. Yeah. Any other question?
So is that an importance of the hyperparameter that you just mentioned? Like which one should we like adjust first? Like you said that we can adjust like step size and like so on. Yeah.
Yeah. So let's say let's
which one is?
Yeah. Good question.
Which one should we adjust first?
Yeah. So that's a great question. Just to rephrase, I guess you're asking, is there a importance across these hyperparameters such that I can focus on the most bang per buck hyperparameters first,
yes.
and then others later. I would say those become rules of the,
we have rule of thumb of that.
I don't have enough knowledge like right now to comment on the fly, but I know. So I know techniques which hyperparameter optimize, which don't give preference to preference across these hyperparameter choices. Like they'll try all of them with equal importance, but I don't know if there is one is more important than the other. Okay, it really depends on the model and the object. So in theory, it should not be the case, but in practice, it may turn out that step size has a much bigger impact on your final model that you pick than the number of gradient descent iterations that you do, or the initialization values that you pick for your model, and so on. So it's unclear. Yeah, I mean, off the cuff, I don't have an answer for that. Yeah.
Okay. And from the chat, Supriya said that step size smaller make it easy to converge. Is that true?
Oh, actually, I really went I will answer that question, but I do want to say, folks, if you want to leave, you can certainly feel free to leave. I'm still recording this because I think the questions are answers are worth recording. Feel free to leave. Also, I am definitely also available online. I'll stay for till if any doubts are getting are there. Certainly stay back and ask. Okay. Now let me answer this question. So feel free to leave. No issues. So back to the question. Step size smaller makes it easy to converge. It may help with convergence, but it has two impacts. Okay, it may slow down the convergence. Maybe you need now 1,000 rounds to converge. Okay, like instead of 200, maybe it's 1,000 if you decrease the step size. But at the same time, if you decrease the step size, you will not jump too far away. So for example, here if I set step size equal 10, okay, I didn't execute this, but let's execute it. You can see, it's all over the place. It's already in step 0. It already went to the bottom. Generally, 0.78 was the lowest value. And then it's jumping out. In fact, it's all over the place. It's in fact diverging. So large step size, you may do pretty badly. Yeah. But if it takes too small of a step size, then you will be, it's unclear, right? So 0.0001, let's say. Then you're still around 1 even after 100 rounds. But if after 200 rounds, but if you do, let's say, I don't want to increase it too much, but say, yeah, now you entered the 90s range after 2,000 rounds and so on. So yeah, that's the impact there. You guys, so actually you have to study this in your assignment. But good questions.
Okay.
Thank you. And in reality, what will be the number of iterations that we will be doing for real-time examples? Like, for example.
Yeah. So I think earlier, I think it was John who was talking about a latest model by OpenAI. I was not sure. Anyway, so
yeah, I think that was me.
Okay.
I remember correctly.
So Sorry.
No, it's fine.
So those types of models, there are other models that we'll see towards, many bigger models that we'll see, and you'll see that actually we are quite limited. We, as in you and the students and myself, we cannot really train models from scratch. Okay, so it really there's a huge computational limit on what we can do.
Okay, but what, like, you might have heard people talking about real-time examples, right? So what would be the rate?
So real time, we just do inference. Okay, so in offline, or generally, there's training part, there's inference part. Inference just means like for a test input, trying to find doing a forward pass. Okay, that also is time consuming, by the way. Just to do inference, just to do a forward pass, you also need GPUs, at least in real time, like Amazon, not Amazon scale, like let's say uh, Spotify and Amazon, they're all outliers, but even a typical ML company which needs ML predictions, they do need GPUs for inference part. Okay, you have a trained model, you just need to make a prediction for, let's say, a new user or something like that. That requires, that itself is, there are certainly inference times you would like to have, like less than a second type of a SLA or something. But training itself, I'm saying that like Atari games, I think I showed you that there was some work that folks did on Atari games back in 2012 so that the computer plays games. So that when they trained it, each game, I think it took about a day, or about a day for 50 days just to do that. But now today, if you want to do the same thing, you can just do it in like a couple of hours. Okay, with the 2012 to 2020, you can do it in a couple of hours. So all this training really depends on the scale of your problem.
Okay.
And sometimes it's impossible to do it by us. For example, I don't know about the DALI code, but it's not even code is not available. But the GPT-3, for example, we know what the architecture is, or GPT-2, which are OpenAI's models. You cannot really train it. It has 175 billion parameters, and you cannot even put it on a single machine, or even a cluster. You need a huge, really large cluster to even put the parameters first, then to iterate on them.
Okay, got it. Thank you.
So it's a huge scale. So we are just really scratching the surface here. Yeah.
Okay.
Yeah. So as I said, so what I'm going to do is now stop recording. And if you have more questions, you can stay back and ask. Thank you.